Okay, in this video we're going to finish up section 2.6, and we're going to deal with the composition of two functions, or composing them together. So the composition of function f with function g is denoted by f, and then we got this little like open circle in there, and then we have g, f compose g, and is defined by this equation. F compose g of x equals f of g of x. The domain of this composite function, f compose g, is the set of all x such that 1, x is in the domain of the g function, and g of x is in the domain of the f function. Now that might be a little confusing the first time you read it, but as we work through an example or two, we should be able to clear up any confusion in there. So the composition of f with g, or f compose g, is illustrated in this figure. First we take an input, x, and we plug it into the function g, and out pops its output, g of x, whatever that is. Well, this output becomes the input of the next function, f of x. And we take the g of x function and we plug it in, and then f does something to it, and we get f of g of x. So again, as far as the domain goes, x must be in the domain of the g function, and this output, g of x, must be in the domain of the f function. The figure reinforces the fact that the inside function, g, in f of g of x is done first. Okay, now this here, I'll call this the inner function. G of x, that entire function, is going to be put into the f function. So that is what I'll refer to as the inner function. What function goes into the other. So let's take this for a test drive. Example 5, forming composite functions. I'll underline in red here f of x, that is 3x minus 4. And g of x, I'll underline in blue, x squared minus 2x plus 6. Now notice here what they're asking us to do is compose this both ways. F of g of x, and then the reverse, g of f of x. And then we're going to evaluate the second one, g of f of x, at 1, g of f of 1. So let's see here, and I prefer this notation for letter A. You know, f compose g of x is f of g of x. And for letter B, g compose f of x, g of f of x. Okay, let's see here. For the first one, f compose g of x, or f of g of x, I'm going to take the g function and plug it into the f function. So let me copy the f function, leaving out the x's. I'm just going to leave it as a gap. So f of x was 3 times something minus 4. Again, this was 3x minus 4, but now the x is gone, and I'm going to replace that x with the entire g function. G, here, the g function is going to be put into the f function. So this g function, x squared minus 2x plus 6, goes in where the x used to be. This used to be 3x minus 4. Now it's 3 times the g of x function, and then minus 4. So let's distribute the 3. 3x squared minus 6x plus 18. And then we have our minus 4 on the end. So then that, if we collect our like terms, just those two numbers at the end. 3x squared minus 6x plus 14. So that is f of g of x. Again, the g function went into the f function. Now let's see, I don't want to erase this. Let me just make it a little smaller here. And then right over here, we'll do the reverse. G of f of x. So the f of x function is going to be placed into the g function. So let me copy the g function, leaving out the x's. G was something squared minus 2 times something plus 6. Again, g of x was x squared minus 2x plus 6. Now the x's are gone, and I just replace them with the empty sets of parentheses. in those empty sets of parentheses, I will put the f function. So f of x was 3x minus 4. So this becomes 3x minus 4 quantity squared minus 2 times the quantity, 3x minus 4, and then plus 6. Okay, it looks like I am going to have to erase this and give myself a little more room. Just remember at the end here, when we see the end result of g of f of x, it's going to look very different from f of g of x. So let me get rid of this. Okay. Because, of course, that 3x minus 4 quantity squared, we're going to have to FOIL that out. And then distribute the 2 and then collect like terms. So 3x minus 4 quantity squared is going to be a 9x squared minus 24x plus 16. And then distribute the negative 2. That'll be a minus 6x. And then a plus 8. And then we got our plus 6 on the end. So collect like terms, 9x squared. And then we have a minus 24x and a minus 6x. That's minus 30x's. And then 8 and 6 add up to 14. 14 and 16 add up to 30. So we have a plus 30. There is g of f of x. So that was letter B, g of f of x. And for letter C now, they just want us to run a 1 through there. G of f of 1. So g of f of 1 means I'm just going to put a 1 in for this x and this x. 9 times 1 squared minus 30 times 1 plus 30. And let's see, the minus 30 times 1, that'll be a negative 30 plus 30, so those wash out. And we're left with 9 times 1 squared, which is 9. And there's our final answer. Okay, and also just a note here, they didn't ask us to, or didn't bring it up, but the domain of that composite function would be all real numbers. F of x has a domain of all real numbers. G of x also has a domain of all real numbers. So when we composed them, f of g of x, that would also have a domain of all real numbers, as would the other direction. G of f of x would also have a domain of all real numbers. Let's see what happens here in example 6 when we have to worry about those domains. So we need to be careful in determining the domain for a composite function. The following values must be excluded from the input x. 1. If x is not in the domain of g, it must not be in the domain of the composite function f compose g. Notice g here is the second one, or the inner function, f of g of x. And 2, any x for which g of x is not in the domain of f must not be in the domain of the composition, f compose g of x. It all comes down to, you'll see in the next example, when we do the composition and we're determining its domain, we have to look at the inner function. Look at the inner function's domain and the domain of the final composed function and look for their intersection, or the more restrictive of the two domains. And you'll see that here in example 6. F of x is 2 divided by quantity x minus 1, and g of x is 3 over x. And it wants us to find each of the following. F compose g of x and then its domain. So for letter A, f of g of x. I'm going to take the g function, wrap it up like a Christmas present, and put it into the f function wherever I used to see an x. So here's my g of x function. Again, I'm going to wrap this up like a Christmas gift. And it's going to go in for this x in the denominator. So f of g of x. The outer function is f, so I'm going to copy the outer function f, leaving an empty set of parentheses where the x was. 2 over, and it used to have x minus 1. But now that x is gone, and the other function is going in its place. So that becomes a 3 over x. Okay, before we worry about the domain, let's clean this up. You know, fractions within fractions is bad math manners. So let's see, if I multiply my numerator and denominator by the same term, I will clear all my fractions. Well, it's easy to see. Our only denominator here is x, so that would be our common denominator. I'm going to multiply my denominator by an x, and my numerator also, just to be fair. So here, x times 2 is 2x. And then in our denominator, this would be 3x divided by x, so the x's would cancel, leaving the 3, minus x times negative 1 is a minus x. So here's our composed function. Now again, the domain of the composed function. We need to look at the inner function's domain and then the final composed function. So let me just rewrite this. This was our f of g of x. Okay, so we have our composed function. What is its domain? First, let's look at the inner function's domain. The inner function is hidden here in this composed function. You know, we compose the two functions together, but the inner function is hidden in there, but we still have to respect its domain. So the inner domain would be our inner function g of x. What domain restriction would we have on g of x? Well, it's 3 over x, so we do not want x to equal 0. So that's our inner function's domain. Now we want to look at our composed function's domain. Composed domain. Well, here's our composed function, and we have a fraction, so we want to set this denominator not equal to 0. 3 minus x cannot equal 0, and if we add x to both sides, we'll get x cannot equal 3. So here is our domain, the set of all x such that x cannot equal 0 or 3. Or if you want to do that in interval notation, let's say it'd be negative infinity to 0, unioned with 0 to 3, union with 3 to infinity. And there we go again, you know, here's our composed function, and it looks like we could plug the number 0 in there, but remember, 0 would violate the hidden inner function's domain. Look to the inner function, and then look at your final composed function to figure out the composed function's domain. All right, and as there's another operation we can do. You know, we're looking at two functions composed together. Well, here we can reverse that process and decompose a couple of functions, pull them apart, so to speak. So here it says express h of x as the composition of two functions. Well, h of x can be thought of as, you know, f of g of x, two functions that were composed together. Well, here's h of x, the third root of x squared plus 1. Well, we can see that we have a radical, so one of our two functions that we're going to break this into is probably going to be our third root function. The third root of something, let's just call it x. And then what is under that radical is our other function, x squared plus 1. So here's our two functions that we can break it up into. We just got to watch out what order we're putting them in, depending on which we call what. You know, here g is the inner function. So which of these is our inner function? Well, this is the one that we would put underneath the radical where that x was. So then this here would be our g of x, and leaving the cube root as our f of x function. So f of x equals the third root of x. G of x equals what's under the radical in our original function, x squared plus 1. So f of g of x would equal the third root of the quantity x squared plus 1, which is what they gave us. That was our original h of x. All right, here's 3 practice problems for you, checkpoint 5, 6, and 7. The first is to compose them and then evaluate here at -1. Number 6 is just like example 6, find f of g of x and determine its domain. The last one is to decompose the functions. So pause the video, try the problems, and then check your answers. All right, for number 5. Here's f of x, here's g of x. Find each of the following. Well, letter A, they want us to compose f of g of x. So g is our inner function. That's going to go into the f function. So let me copy the f function without the x's in it. F was 5x plus 6. But now that x is gone. That x is going to be replaced with the whole g of x function. And g of x was 2x squared minus x minus 1. So let's see, distribute the 5. That's going to be a 10x squared minus 5x minus 5, and then we have our plus 6. So when we combine like terms, 10x squared minus 5x plus 1 would be our final answer. Okay, now we're going to go in the other direction. That was f of g of x. Now we're going to do g of f of x. G of f of x. Again, so g is the outer function. I'm going to copy the outer function without the x's in it. See, g was 2 times something squared minus that same something minus 1. Now I'm going to replace those x's. You know, there used to be x's here in the g function. But now I'm going to replace those x's with the f function. 5x plus 6. And let's simplify it down here. So we're going to have our 2, and if I FOIL this out, I'm going to get a 25x squared plus 60x plus 36. And I'm going to leave this in parentheses for now, because I do have to distribute this leading 2, and then I'll distribute the negative across that second set of parentheses. So let's see, that's 50x squareds plus 120x, wow, plus 72 minus 5x minus 6 minus 1. So let's collect up our like terms. Here's our only x squared term. So that's 50x squared. And then we have a 120 minus 5, that's plus 115x. And then those add up to a minus 7. 72 minus 7 is 65. So there's our final answer for g of f of x. Now let's see, the first one, or letter C, is f compose g of negative 1. So I guess after we did A, we should have done part C, because this negative 1 goes into our first answer up here. And let's see, what was f of g of x? That was 10x squared minus 5x plus 1. Yep, and we're going to plug in a negative 1. F of g of negative 1 is going to equal 10 times negative 1 squared minus 5 times negative 1 plus 1. See, order of operations, we do exponents first. We square that and get a positive 1. Positive 1 times 10 is 10. Minus 5 times negative 1 will turn into a plus 5, and then we have a plus 1. So that all adds up to 16. And that's our answer for part C. F compose g of negative 1 is 16. Let's see here for number 6. Here's our f of x function. Here's g of x. Find the following. The first is f of g of x. So my outer function is f. I'm going to copy f, leaving out the x's. So it was 4 over x plus 2. But now that x is gone, and I'm going to replace that x with the g function. And the g function is 1 divided by x. Okay, it's looking a lot like our example. So I'm going to multiply my numerator times x, and I'm going to do it to the denominator to clear the fractions. So my numerator is now 4x divided by, here the x's cancel, and we're going to be left with a 1 plus, distribute the x to the 2, plus 2x. So here's our composed function, f of g of x. And let's see, it wants us to also find the domain of that function. So the domain. First, we look to the inner functions domain. So the inner function here was the g function. So let's look at the g function right here. G is 1 divided by x. So of course we want x to not equal 0. So x cannot equal 0 for that. In the second part, we do not want our denominator to equal 0. So let's see here. Here's the now this is our composed function. We looked at our inner functions domain. Now our composition looks like this. 4x divided by the quantity 1 plus 2x. Well, we want that denominator, 1 plus 2x, to not equal 0. So let's see, let's solve for x here. If I subtract 1 from each side, 2x cannot equal negative 1. And if I divide by the 2, x cannot equal negative a half. So here are our two restrictions on the domain. We cannot have it equal 0, and we cannot have it equal negative a half. So the easiest way, I guess, to write it would be with set builder, the set of all x, such that x does not equal negative a half or 0. Or you could also do that with the interval notation. Interval, we'd start at negative infinity and go to negative a half, and then union that from negative a half to 0, and then union that from 0 to infinity. And there's our domain of the composed function. Remember to always check that inner functions domain. That inner function is hidden in the composed function, but we still have to respect its domain. Okay, here express h of x as the composition of two functions. So h of x is going to equal, let's just go back to f and g, f of g of x. So there is some inner function that we ran through an outer f function. Well, here it looks like my outer function is going to be a radical. So let's say f of x is the square root of something, and we'll just call it x. And then g of x, what are we square rooting? Well, that's the quantity underneath, x squared plus 5. So if we did put the g of x function into the f function, we would get back to where we started at, h of x, square root of quantity x squared plus 5. All right, here's a handful of problems to keep you busy on page 298. Have fun.